Welcome and hello. This is a video tutorial on HEC HMS, and in this lesson, I'm going to be talking about the energy balance snowmelt method. This is within subbasin editing. So within subbasins, we have to specify snowmelt if there's snow in the simulation, and then the energy balance and gridded energy balance are two different options for us to calculate the snowmelt. What I have on the screen here is my watershed, and it's already been delineated into multiple subbasins. I'm going to go ahead and zoom in on the downstream location, specifically these two subbasins, 45 and 44. Now for 45, I'm going to select I was already selected. I'm going to come down here to the components editor, and for snow method or snow melt method, select energy budget. Our options are none, energy budget, gridded energy budget, temperature index, gridded temperature index, and gridded hybrid. So for this lesson, I'm going to be talking about energy budget and gridded energy budget. That's interesting because the user's manual calls it energy balance. I, I'm not kidding. It's called an energy balance here. So anyway, I'm going to try to call it energy balance, but it's the same version too, 4.12. So anyway, energy budget, energy balance. Let's carry on here. So the energy budget or energy balance snowmelt method is a energy balance model is a physically based energy and mass balance model. The model represents the snowpack as a single layer and considers the thermal interactions between the snowpack and its surrounding environment. What I have to do here for using the energy budget snowmelt method is to specify elevation bands, or at least one band. So what that means is I'm going to click on the snow tab, and then here is some data I need to provide, and we'll do that as well. In the watershed explorer here, I'm going to expand, and I have energy budget selected. Then I'm going to right click and say add elevation band. And then if I expand that, I see band number one. And then I can add more bands if I want. I could just keep adding bands. One, two, three. I can delete bands by right click and remove band. And there's a delete confirmation there as well. So I can only delete the last one I've added apparently. If I select on a band, then it gives me information about the band. And what these bands are is it's basically an area within the subbasin that is between whose ground elevation is between a certain elevation range. So for instance, you need at least one of these elevation bands using the energy balance and energy budget snowmelt method. And you may only need one if the terrain is very flat, but if there's a lot of variation in the elevation of the terrain within that subbasin, then you may want to use multiple bands because those initial conditions could be very different and hence affect the simulation of snowmelt. Let's just talk about these. The percent here is the percent of area. So for instance, if it was 50% in band one and 50% in band two, that's fine. It doesn't necessarily have to be conterminous or contiguous areas. You could have, different areas as different bands. This is just the overall area percentage. I'm going to work with band one though. Okay, so elevation is the next one. This is really an average elevation for that particular elevation band. For elevation, you can use an area weighted elevation for all the area within that band. You could just take an elevation average between the minimum and the maximum. That's kind of up to the discretion of the modeler. The next field down is slope, and this represents the average slope for that elevation band. Again, you can use like an area weighted or average the min and the max. Again, that's kind of up to the modeler. And then the next is the aspect in degree. This represents the average aspect of the elevation band, or in other words, the predominant downhill direction for that elevation band within the subbasin. For this value, 0 degrees is due north, and then as you rotate clockwise, it increases. So you could say northeast is 45 degrees, due east is 90 degrees, southeast is 135 degrees, and so on. And it doesn't have to be on a 45-degree increment. It can be whatever integer degree, I presume. All right, the next field down is our precipitation index, and this is really the only non-required field, but you could fill this out if there's a lot of variation of precipitation between the different elevation bands within the subbasin. But if you do fill out this precipitation index field, you, by the way, need to also fill it out for all the bands and then also for the subbasin, which would be right here. Okay, so the next one is initial snow water equivalent in inches. And I'll just say that the rest of these are about the initial conditions of the snow. So if there's no snow in the model at all, you probably don't even need snow melt, or if it won't snow during the simulation. But if there's no snow to start the simulation, you could just type in 0 for the snow water equivalent, 0 for the initial snow depth, and then let's see, if there's no snow, I think you just use 32 for Fahrenheit and or 0 for Celsius, and then yeah, 0 for these values as well. But if you do have snow at the beginning of the simulation for the particular selected band, you would type in the initial snow water equivalent. That is the depth of water that would result from all the snow melting in that elevation band. And the initial snow depth is similar. This is the depth of the snowpack. So, for instance, it's in inches. So if it's like 10 feet, you type in 120. If it's like 5 feet, it would be 60 inches. Now, remember, this is like an average, so it's over the entire area of the elevation band, which means it would be an average or some sort of interpolation based on field data from snow surveys. The initial surface temperature is the average ground temperature in the elevation band at the start of the simulation. And again, that's determined using averaging methods. And then the initial snowpack temperature, just below it, Fahrenheit, is the average temperature of the snowpack at the beginning of the simulation. Again, that's determined by some sort of averaging and snow survey sampling. The initial snow albedo represents the fraction of incoming solar radiation that is reflected by the snow surface. It is a dimensionless quantity that ranges between 0 and 1. And lastly, the initial liquid water fraction is the percentage of snow that is in liquid state. This would only occur if the snow pack is at a melting temperature. But the value would be 0 if there's no snow or if the air temperature has been sufficiently below freezing for a sufficiently long time. All right, well, that is it for the band data. Again, this needs to all be filled out for all the bands. Next, I want to talk about the snow melt parameters for the entire subbasin. So if you click on the subbasin and then click on the snow tab here, we have all these data fields. So let's talk about these. Precipitation index, we already touched on, that dealt with the variation of different amounts of precipitation across different elevation bands and subbasins. The next two fields are the rain threshold air temperature and the snow threshold air temperature. So if the air temperature itself is higher or larger or warmer than the rain threshold air temperature, then all the precipitation is going to be rain. If the air temperature is less than the snow threshold air temperature, then all the precipitation is snow. And if the air temperature is between the rain threshold and snow threshold air temperatures, then the precipitation would be a combination of rain and snow. And that just depends on the actual values of all those air temperatures. The next field is the albedo method. And I don't have an option here. This Kondo and Yamazaki is the only option to use. So that's the one we'll use. Next, we have new snow albedo. This represents the reflectivity of newly fallen snow, and it ranges typically from 0.8 to 0.95, according to the user's manual. The next one down is the minimum snow albedo, and this represents the lower limit of the reflectivity of the snow, and the range is there from 0.2 or to 0.5 typically. The next one down is the albedo refresh depth, and this is in inches. This represents the depth of fresh snow required to reset the albedo to the new snow albedo value. Albedo decay coefficient method and the albedo decay value are the next two fields. So my options here are either a fixed value, which is the default, and if I choose that, then I just type in my number. It's probably not one though. And then the other option is an annual pattern. So for fixed value, that means it's the same all year round, but annual pattern means that it would change throughout the year. So I'll go ahead and select annual pattern. Now what it's asking for is an albedo decay coefficient pattern. And currently I don't have any patterns defined. So let's go ahead and add one. To do that, let's head up to the Components menu and then Paired Data Manager. Next, I'm going to select the data type and I'm going to come down to the Parameter Value Patterns and then click New. Give that paired data set a name. I'm just going to call it albedo decay 45 for subbasin 45 and then create. Okay. Now up here in the Watershed Explorer, I have a paired data folder and a parameter value pattern folder. And then here's the paired data set that I just created, albedo decay 45. Down here in the components editor, I need to specify the category is Snowmelt. I am using energy budget, but there's also temperature index, so not energy balance, I guess. And then the parameter is albedo decay coefficient, and then I can select the units. If I'm using the manual entry, then I could just type the values in here. So again, this is over the course of 12 months. So I'd probably start with January 1 at 0, hours. And then whenever it changes to a new value, I would create a new row in this table. There's also a graph here to show what that table data would look like. If I select the HEC DSS, then I would just select that value and then navigate to the particular file name and name. All right, let's go ahead and see if that works. So I'm going to go ahead and click Save Subbasin and then Snow. And then if I select Annual Pattern, then I can select Albedo Decay 45. So perfect. That's what I was looking for. Snow thermal conductivity is the next field. It describes the snow's ability to conduct heat and is used to calculate the snowpack surface temperature flux. The liquid water retention fraction is used to compute the portion of energy content held as liquid water in the snowpack. The next field down is the snow hydraulic conductivity. That's right here. It is used to calculate the liquid water content in the snowpack in Darcy's law for flow through porous media. And then the last one here is the soil depth for energy balance. That's in feet or length. And it is the depth of soil that interacts thermally with the snowpack. So these are the fields that we need to define when using the energy balance snowmelt method for subbasin in HEC HMS. The user's manual specifies another requirement when using both the energy balance and gridded energy balance methods. It involves setting boundary conditions in the meteorological model that's linked to this particular basin. So we're talking about subbasin 45 so far, but the meteorological model will be applied to the entire basin. So let me just go to the top of the Watershed Explorer, and we have a basin here. It's basin 1. What I'm going to do is go up to Components and then Meteorological Model Manager. I'm going to click the New button, and then I'm going to paste in a name for this model. Click Create, and then close that. Now up in the Watershed Explorer, I have a meteorologic models, and then here is the model I just created. Now I have to specify this data right down here. The user's manual says I need to specify the incoming shortwave radiation, incoming long wave radiation, that's here, precipitation, temperature, wind speed, atmospheric pressure, and relative humidity. When all that is done, then I also need to specify the actual basins. So I only have one basin, which has 45 subbasins, and then select the value of yes here, and then save. What we did here is select base subbasin 45. We signed it energy budget or energy balance snow melt method. If I wanted to see all the subbasins that have that particular snow melt method assigned, I can go up to parameters, snow melt, energy budget, and then here I have what is called a global editor. I can see all the different subbasins listed. There's only one, and then all the values. And then these values can be edited right here. Also, there's a few fields over to the right. Of course, a lot of these fields are empty because I was just talking about them, wasn't actually filling out data. All right, so I'm going to go ahead and close that. Let's head over to Subbasin 44 and briefly talk about the gridded energy balance snowmelt method. So let's select our snow method and gridded energy budget or energy balance. I'm still not sure what it's called. And go ahead and click save. If we go ahead and expand the Subbasin 4, we have gridded energy budget right here. And if I right click, I cannot add the elevation bands. And that's how it's supposed to be because the gridded energy budget now depends on a grid of data across the subbasin area, not elevation bands. The gridded energy balance method is the same as the regular energy balance method, except that the equations for simulating the snowpack are computed separately for each grid cell with separate precipitation and temperature boundary conditions instead of an area averaged values over the whole basin. Just like the energy balance snowmelt method, we can go up to parameters, snowmelt, and then select gridded energy budget. Here we see all the fields that are associated with that snowmelt method, and we would see all the different subbasins that use that snowmelt method. Also, when using this method, we need to perform the same meteorological model that we did before and select the yes for the basin, as well as fill out these fields here. Okay, let's go back to the snow tab. And the only difference in this list of fields here is the initial values. So everything from rain threshold, air temperature down through the bottom is the same as the energy balance method. But in the gridded energy balance method, we have initial values in either default or parameter grid. Now, all these fields here in parameter grid is really the purpose behind using a gridded version of the energy balance snowmelt method. If we just use default values, then the user's manual specifies what those values are. So for instance, it would just be a constant snow water equivalent of 0 millimeters or 0 inches. It would be a constant and initial surface temperature, and that would also be 0 Celsius or 32 Fahrenheit. Again, the user's manual would tell you what those default values are. But if you selected parameter grid, then you would also be expected to fill out or provide a grid for each of these 7 different parameters. And this is all for the initial snowpack across the grid of the sub basin. So let's do one of these just to show what that means. The first one here is initial snow water equivalent grid. I'm going to go up to components and then grid data manager. Then I'm going to select the type of as snow water equivalent grids, and then click new. And then for the name, I'm just going to paste in a name and create. All right, let's go ahead and confirm that that was created. So now I have a directory here for grid data, and snow water equivalent grids is a subdirectory, and SWE44 was the name that I provided. Next, I need to provide a data source, so I can either provide a single DSS file, multiple DSS files, an ASCII file, or a GeoTIFF. And then based on that data source selection, we'd have to fill out a few more fields. Let's go back to confirm that that worked. I'm going to select Subbasin 44, the Snow tab, and then for my initial snow water equivalent grid, I can now select that SWE44 grid dataset that I provided. All right, well, that's about it. There's obviously 6 other grids that we could be doing. For instance, initial surface temperature grid. You do the same thing. You'd go up to the components editor, select grid data manager, and then for the type, you'd select temperature grid set, and then give it a name, and then fill out the data. And then you'd be able to select it here, and so on. When using the gridded energy balance snowmelt method, the user's manual mentions that you can perform the terrain pre-processing. So what that looks like is if you go up to your Watershed Explorer, click on terrain data, and then select the terrain data record that is assigned to the basin model. You can go right click and then pre-process slope and aspect as well as pre-process solar shading. So I performed these tasks. The pre-process slope and aspect was really quick, but then the pre-process solar shading was really slow, and I didn't even wait for it to finish. For solar shading, the value would be 0 if it's full shade, and the values would be 1.0 if it's in full sun. Well, that's it for this discussion on the energy budget or energy balance snowmelt method, and also the gridded energy budget or energy balance snowmelt method here in HEC HMS.